So now we pick up again on our second presentation, which will be given by Zheng, Global Solutions for a Silent Poison, Human Health Risks of Arsenic in the Mekong River Delta. It's a different dimension from our previous presentation. It turns towards groundwater quality and human health, a very relevant aspect of delta management, as we've seen in some of our previous presentations. So Yang, you have 25 minutes.
All right, thank you very much for this opportunity, and thank Professor Qing Yunduan, who alerted me this opportunity many years ago before COVID, and then we're finally here in the Mekong Delta. So without further ado, I'll just go ahead and get started. But that is the library of SUSTEC. We're located in the Pearl River Delta, another one you saw in the former presentation of Jennifer. So my presentation has 3 parts. First, I will just say a few words about why groundwater is so important. And then I will share with you some of the work we did in other regions of the world where faces groundwater arsenic challenges, including the United States. And finally, I'll report to you the work we did in the Mekong River Delta, but primarily in the Cambodia area. Just to start, groundwater, like surface water, follows the gravity, which flows from high places to low places. And so that's the part 1. So several years ago, after AGU Chapman conference, a whole bunch of hydrogeologists got together and released this global groundwater statement. And there are essentially 4 reasons why we should care about groundwater. 2 billion people drink it, and 40% of the irrigated agriculture rely on it. But we also have poor water quality issues, which tend to affect poor people more, which you will proceed to see in this talk. But not known to many people is that groundwater is actually the base flow, which is extremely important for ecosystem, and that since groundwater is so important, we haven't been protected very well, and therefore it's being overused. So I'm really glad that I heard people here working on nitrate problems, because groundwater quality problems, unless like arsenic, which comes from the sand and the clay that makes up the aquifer, we call them geogenic problems. Most of the groundwater quality problems are due to either agriculture or industrial or just simple living in urban areas. Humans have not built any infrastructure that does not leak. In UK, more than half of the groundwater recharge in urban areas come from leaked sewers. And obviously, in irrigated agriculture, irrigation return flow tend to dominate the groundwater recharge, and come with that, you have everything you can possibly wish for in your recharge water. So, but there are people also like us. I'll get to this in the very end. I also brought a book to donate to the university. I initiated the managed aquifer recharge in Bangladesh while I was with UNICEF WASH. Because we obviously need to replenish the overdrafted groundwater, but that's very tricky. I'll get to that. So since the groundwater statement was released, it has put groundwater on the global water agenda, and the UN Water Conference, people had a strong showing, followed by Groundwater Summit. So groundwater people is making progress, making this very invisible resources more visible to the global water community. So if I want to make one takeaway point today, is I wish the Rosenberg Forum in your considerations place more emphasis on groundwater sustainability and protection. So we also have an urgent need to train more hydrogeologists. Actually, I taught in US universities, trained a lot of students. All of them went to industry because it pays better. There is actually a shortage, always a shortage of very well-trained groundwater people. So now I'll come to some of these solutions to this poison and started with work. I'll talk about Bangladesh and United States and China. And in 2020, Podolsky and Berg, both of EWAC, published this machine learning model that made a prediction of where groundwater risks are in the entire world. And you can see Asia is where most of the exposed population reside, in West Bengal, India, in Bangladesh, and also here in parts of the Mekong and Red River Delta. And Science invited me to write a perspective article to go along with it. And I should emphasize this is a data-driven model, and therefore data is the key, and data, we have huge data gaps. But if you look at arsenic, why do we care about arsenic? At current, WHO has recommends 10 microgram per liter as the guideline value, but you should understand that is not based on health. It's one of the very, very few drinking water quality standard that's not health-based. This is based on cost compromises. This is in 1 in 10,000 cancer risk instead of 1 in a million. And over the years, in collaboration with public health scientists at Columbia, we have come to discover a huge amount of non-cancer health risks, including cardiovascular diseases and diabetes, as well as children's IQ effects. So arsenic is all around poison. Not only it can kill you, but it can also make you dumb. So in that article, and many others. What should we do? It turns out the model are useful, but model can be very wrong. But you can prioritize these high arsenic areas. You should go test. And once you have some results, you need to test wells really close to each well you identify, because your chances of finding other arsenic wells significantly increases because we are resource constrained. And in this time, there are a lot of methods that you can test arsenic in the laboratory. We still urgently need really reliable and inexpensive method to test arsenic in the field. So in New England, my group's been working first in Maine, then later in New Jersey. And by 2016, I used to go to Maine State House, do these hearings. After a lot of politicking, this Maine legislation passed this piece of legislation that established a private well water fund. Essentially, instead of requiring people testing their well water for arsenic, it actually provides a little bit of money to enable poorer households to do so. It's the step in the right direction. What we really would have liked to see is a requirement to test this, because our study in New Jersey has found by requiring testing arsenic when homes are exchange hands, you double the rate of testing. And I like to joke with my students, arsenic is like the perennial bush. Even after retire, when I go back to United States, the problem awaits me, because in the US, all the private well water is your own business. You are responsible for your own water quality. It's your own business to ensure it's tested and meets all the standards. And many people do not do that. And even in places we worked a lot, the testing rate is only half. So we also looked across the entire US. You can look at the states that has requirement. It's essentially a hodgepodge of everything possible. Very few states, 40 million, 45 million people drink from private well. And census has stopped asking this question, so we don't know how many people rely on private well for their drinking water anymore. But if you believe what USGS and USGS good colleague Joe Ayotte has also done similar machine learning models, it's about 10% of chances you will be exposed to arsenic. So millions of people in the US. So in China, this was a big problem. People were dying from it. So in the early 2000s, I was invited by UNICEF and worked with the Chinese CDC. And the Chinese approach was the opposite one, because people were getting sick So these are doctors leading people to villages, more than 8,000 of them. They had the villages, had the water tested, and a huge campaign of changing water sources began right around that time. So by this time, 75% of these villages had got new water sources. But we still use these high arsenic water for irrigation, which then gets accumulating in the soil, which then gets into the rice. So in Yinchuan Plain, to make a long story short, we worked on in situ removal methods that can actually create a filter by the well. So when you pump, your water is become arsenic safe for irrigation. I wouldn't recommend this to a lot of people unless that's your only choice of irrigation. I think you wanted to find other alternative source water. And likewise, treatment can be very successful. We simultaneously deployed this solid phase base because you need to pre-oxidize arsenic into the right form in order to be removed, which was a headache in a lot of the applications. So in this, we actually changed the material. So we have solid phase-based oxidant and sorbent, and we deployed that in New Jersey and in rural China, which was successful. But again, I don't wish it on anyone to have to do this unless you have to. It's expensive. So the best way is to actually find alternative replacement water sources to avoid it. The reason you need to avoid it is because when I was with UNICEF Bangladesh following my colleague who was with WASH UNICEF, Rick Johnston, he's now with WHO, we pushed for the first drinking water quality survey nationwide. And we tested arsenic and other things. And my colleague at Columbia sent Sarah Flanagan, a master's student who came, and we looked at the mortality rate exclusively attributable to drinking arsenic water, and that's 1 in every 18 adult deaths. And this paper had a lot of impact on driving the policy. I think this is what convinced the Bangladesh government that it really needed to do something. So what do? You can drill deeper. It turns out the deeper groundwater, as you can see in the map, particularly in the high arsenic area close to the delta, has much, much lower probability of arsenic occurrence. All the science is in those papers. If you're interested, I can tell you. But I do want to mention we also did injection experiments. That was the work by Carrie Redloff. She was a student at Columbia. And we did modeling to simulate if you use groundwater only for drinking, this can be a sustained source for thousands of years. However, if you start to pump this low arsenic water for irrigation, you will have a risk of contaminating that aquifer and therefore not recommended. So therefore, you need to develop this deep aquifer resource really carefully. So finally, this brings me to the Mekong Delta. This project was funded by the Chinese Academy of Sciences, and we have a book that's open access. And this is part of the work, chapter 4. I will start with that, which we were asked to do an arsenic risk assessment for the Mekong Delta. And here, I fully agree with Jennifer. In this book, I need to define the delta. I define the Mekong Delta by sea level 10 meter. You can agree or disagree with me. That's the green thing. And I also should acknowledge the Resource Development International in Cambodia, an NGO, particularly Miki Sampson, who spearheaded a lot of this testing, which fed into this, and Vietnamese Department of Water Resources, which also tested about 50,000. So altogether, we had about 100,000 water testing data points. And those are some of the field pictures. You can see one of the tube wells that people will use. And then people will also use this water for irrigation. But bear in mind, there is also abundant surface water. So I think we need to really think about what you use. So here are these results. Again, using the method similar to population attributable fraction. So the way you look at this data is basically those corresponding, you have higher dose, you have higher death rate. So we can estimate the excess deaths. And in Vietnam, I think there are 3 districts very close to Mekong River that has very, very high risk. So I'll break it down for you a little bit. Unfortunately, the Mekong River Delta's geology is fundamentally different from the Ganges-Brahmaputra Delta. It doesn't really have a very well-developed deeper aquifer. And in fact, in Vietnam, it's still controversial why this deeper groundwater still has occurrence of arsenic, different hypotheses being proposed. But they are there. So it's lower probability, so you can probably use it, but combined with testing capacity. And then definitely the sediment that has arsenic appeared to come from upstream. In fact, many years ago, I had another project up in Tibet where we looked at the river transport of arsenic-bearing sediment and made a calculation about a quarter of arsenic-bearing sediment in the Mekong Delta is supplied by the Lancang River from Tibetan Plateau, and it's geothermal sourced. So very close to the river, that's the reason, because it's transported from up gradient and therefore closer to the river, either Mekong or Bezak. We always told, our guide told us there are 2 rivers, and that's where the risks are. And then there's also clearly a risk with elevation. So below 25 meters above sea level, you start to see, and this is consistent with our understanding of arsenic release mechanism, slow moving groundwater, reducing conditions and mobilizing the arsenic in the iron oxide phases into the water phases. And you will note that in Mekong River, the concentrations of arsenic can be extraordinarily high. Bearing in mind it should be below 10, and the Dutch has voluntarily lowered this to less than 1. So we also looked at the rice risks, and so we collected rice samples and also soil samples. While we analyzed this large database, we clustered them. So we have a low groundwater cluster in blue, and then the really high ones in red. And then we looked at the rice arsenic and soil arsenic. And as you can see, with the groundwater, when they are in high groundwater arsenic area, the soil arsenic clearly increases. There is a really interesting detail. The soil arsenic also increases in MMA, which is also a toxic form of arsenic. Typically, we tend to think inorganic arsenic is toxic, but thank goodness the rice grain seems to have a mechanism protecting themselves. So therefore, it does not contain that. And DMA in rice, you can think of it as the non-toxic form. So with that in mind, we looked at all the rice speciation data, because when you look at the rice arsenic safety, you basically wanted to know how much of that is inorganic arsenic. And you can see that in the low groundwater area, it kind of tapers off, but in the high groundwater area, the majority of the arsenic is inorganic. So that's really bad news. So if you use high inorganic arsenic groundwater to irrigate your rice, you will wound up even more toxic rice, because typically when it comes to regulators, most of the places only measure the total. They do not. They make assumption about the proportion, but you need to know these characteristics about this rice. And we looked at the global data set. Data are very limited, but it's also similar. In European, this is a big problem. So I wanted to kind of move away a little bit to talk about the groundwater sort of the depletion problems. I don't know if this plays. Is supposed to be a video, but it doesn't play. It was supposed to show how Amsterdam use sand dunes to store aquifer, and we heard about Netherlands deltas and everything. So I think there's a lot to be learned about that. And for this, I brought this book. I'm also one of the co-chairs of IAH, International Association of Hydrogeologists. We have a managed aquifer recharge commission. So we are a small group of people who are interested in recycling water. Okay, any kind of water, put it underground to enhance storage, to purify the water. So a few years ago, UNESCO asked us to produce this book, which we summarizes 28 cases globally. And I can show you where they are, but different people use different source water. blue is natural water or river water, and river water tend to have a lot of reclaimed water in European. And then we have riverbank filtration, which is very popular way of supplying water in Europe, as well as well injection methods, well spreading methods. So I'm happy to give a fully other talk about this, but I do want to bring you back to the initial slide that I showed you about this Bangladesh Myanmar, where in Bangladesh, in all the coastal aquifers, saline, brackish. So what we did more than 15 years ago now is we created a little freshwater bubble as a storage, tiny storage, a few hundred cubic meter, but it's quite cheap. And now this is fully localized. So people can do this themselves. We started with 20 projects, and the Dutch embassy funded another 100. But what keeps me up at nighttime is of the 20 schemes we built when I was working for UNICEF, 2 of them had high arsenic. So again, you're working in arsenic countries. So if you were to do this in the Mekong River Delta, then you better have some water quality, particularly arsenic testing capacity. So this is my recommendation. So now that we know this groundwater arsenic risk area, it's pretty well mapped out. So I urge the Mekong River Commission to prioritize safe water supply in these areas, at least to look into them. And we need to have a plan to move away of irrigated agriculture, because you put arsenic on the soil, you're never going to get rid of it. It's just going to stay there for a long time. It doesn't evaporate, okay? And whenever you are planning for groundwater dependent, for example, if you want to do MAR, because you are in an arsenic risk, high risk area, evaluate arsenic risks. And finally, we need more students, hydrogeology, water quality people, need to build testing capacities here. So this is how you find me. And thank you once again.